Hello, everybody, and welcome to your Earth Science Lecture number 18. This one is on earthquakes. I'm going to be talking about all the different kinds of earthquakes there are and also some few examples of historical earthquakes. So the one that you see in front of you right now is San Francisco, 1906. That was probably the most destructive earthquake in the United States in U.S. history. So 1906, quite a long time ago, of course. And it actually wasn't the biggest earthquake. There have been bigger ones, but I'll show you a little bit more about that San Francisco earthquake soon. So, what causes earthquakes? So, first of all, what the heck is an earthquake? Earthquake is just ground shaking, caused by seismic waves. So seismic waves are just they're mechanical waves. Actually, they're acoustic waves. It's the same as a sound wave. A sound wave, it's just a mechanical wave. It's just vibrating, basically vibrations of the air. That's what makes sound. You can hear sounds that transverse not only through the air but also through the solids. Like if you ever put your ear to a railroad track. Some people have done this. You put your ear to a railroad track. Your friend stands a little bit far away and bangs on the rail. You can hear two sounds. Okay, one is the bang, the clang from the hammer traveling through the air. Another is the clang of the hammer traveling through the railroad track itself. So, materials can solid materials have mechanical waves that can transverse through them just as much as air. So really, it's kind of funny, but an earthquake is really just kind of what would be a very deep, low sound wave, and very loud sound wave, traveling through the earth. Of course, we don't hear it because the frequency is too low, but maybe we could hear it theoretically. But anyway, there are two causes of earthquakes. Okay, some are natural, right? So some are just originating from tectonic forces. We studied plate tectonics already, so you know what I'm talking about. But tectonic forces, moving the land either up or down or left or right, right? So this is a fault. This surface you see right here, this shear face cliff, is actually a fault scarp. So the land here went down. This part of the land went up due to plate tectonic forces. Volcanoes also cause earthquakes. We'll talk about volcanoes next time. There's also human-induced earthquakes. Some induced earthquakes have been from hydraulic fracking. Actually, not the fracking itself, but the pumping, high-pressure pumping of wastewaters deep into the earth kind of lubricates the fault plains and induces some earthquakes. Not big earthquakes, but has induced earthquakes before. Maybe the biggest one being about 5.6 on the Richter scale. So another final cause of earthquakes also is I have Kim Jong-il here, so from North Korea, because he likes to detonate nuclear bombs, test them underground. So nuclear testing can also create earthquakes as well. So tectonic earthquakes involve frictional sliding along a planar surface. So here's your planar surface right here. Okay, that's the planar surface. This fault block moved down. This fault block moved up. This area I scribbled in is called the fault plane. Okay, that's the fault. Whoops, made a B instead of a P. Fault plane. Okay, so that's the fault plane. Now, when there's sliding motion along this fault plane, an earthquake often occurs. Okay, because when you have movement between two fault blocks, it'll often create these seismic waves, these vibrational mechanical waves that propagate through the rock. Okay, so when do earthquakes happen? When is there motion on fault blocks? Okay, I'm going to explain this. Kind of a mouthful, but this is what happens. When tectonic stress exceeds the frictional strength of the fault plane contact, that's when movement will occur and it will generate an earthquake. Okay, so you can imagine there are two fault blocks right here. This is fault block 1, fault block 2. Here's the fault plane. Now, along this fault plane, there's some friction. Okay, So when the tectonic force I'm going to put force. I'm going to put a T, subscript T down here. When the tectonic force is greater than the friction, there's going to be movement along the fault plane. Okay, there'll be movement along this fault plane. That, in turn, is going to generate these seismic waves that will propagate through the rock. That's an earthquake, right? That's the propagation of these seismic waves, the vibrating waves. That's what causes the shaking that we know as an earthquake. So back to San Francisco, 1906. So what happened was that there was massive movement on the, probably a fault you've heard of, San Andreas Fault, which runs right through San Francisco. This created a pretty devastating earthquake. It was actually probably only a magnitude 7 on the Richter scale. It's not the biggest kind of earthquake. Earthquakes can be 100 times bigger, with the magnitude 9 being the largest we've ever experienced in human history, at least recorded, human history. So it's actually not the biggest earthquake that we've ever experienced in the United States. The biggest earthquake there's ever been in the United States was Alaska, 1964, which is known as the Great Alaskan Earthquake. That was a magnitude 9. One of the biggest earthquakes ever to be recorded in human history. So San Francisco, 1906, though, was more devastating because it ran right through a very populated area. Alaska is not, it's more sparsely populated, so it wasn't as devastating. But you could see that the city here is just razed to the ground, not only because of the shaking itself, but because it broke many gas lines that then ignited the city into flames. Here's Stanford University's Memorial Arch before and after the earthquake. You see the arch was decimated. This is another picture I just thought was funny from Stanford, where this august professor's statue was toppled over and he went head first into the ground, sticking up like that. It's kind of amusing. This is San Francisco City Hall. You can see totally hollowed out and destroyed by this earthquake. So it was amazing because San Francisco, of course, is a big city. Was a big city back then. And just to have a city totally razed to the ground like this, it was pretty, you could imagine. You could imagine what that was like. And, it's funny because actually one of the greatest natural disasters in United States history, the hurricane that hit, it was actually like Galveston area, it's killed 4,000 people. That was around the same time as this quake, so it's kind of funny that two huge disasters around the same time. So anyway, the San Francisco earthquake in 1906 was very important historically because I should say the history of seismology. Seismology, by the way, let me spell that out for you. You should know that word. Seismology is the study of seismic waves or earthquakes. Okay, so this is kind of the study of earthquakes. It's one way to think about it. So, of course, people really wanted to understand this earthquake after it happened because people were like, well, is this going to happen again? What caused this earthquake? Do we need to relocate the city? Is this a safe place to live in? So, one of the great early seismologists, Harry Reid, 1910, went to work on these questions and tried to investigate the causes of the earthquake. Of course, people didn't really have much of an idea about what caused earthquakes at this time. This was a very new science, and we didn't know about faults. We didn't know about kind of movement on faults, anything like that. So one of the observations that Harry Reid made, is that there were a lot of displaced fences like this. So fences that had, of course, once been connected had now been moved, significant distance apart after that earthquake. So that was kind of the first example showing, hey, the fault blocks are moving. The land is actually moving. That's what's generating the shaking. Okay, you can still see this around San Francisco. This is in Hollister, which is pretty close to the Bay Area, San Francisco area. You can still see to this day fences displaced by the San Andreas Fault. The San Andreas Fault, or one of the minor faults associated with that system, is running through there. Okay, so let's talk a little bit about the leading theory that Harry Reid came up with to explain how and why earthquakes occur and why they occur kind of in the same place year after year. So this is called elastic rebound theory, and this is a theory that still holds to this day. So, there are faults, and what basically happens is that on these fault blocks, so the fault blocks, you can see 1, 2 fault blocks here. Here's fault block 1, here's fault block number 2. They're separated by a fault. And a fault, very simply, a fault is just a crack in the earth. It's just, a break in the crust where the movement can occur. So what happens is that tectonic stress starts to build up. And as it builds up, you can see that the land begins to deform. Do you see how there's kind of this wavy deformation to the land? So maybe that fence used to be straight, but now it's kind of curved a little bit. Okay. So this is kind of the build-up of tectonic stress in the land. Now, at a certain point, the frictional strength is exceeded by the tectonic force. And again, when tectonic forces exceed the frictional strength, the friction on the fault plane, here's our fault plane right here, okay? When frictional strength gives way to tectonic force, that's when movement occurs. And when the movement occurs, that energy that was being stored up, kind of elastically stored up in the ground, in the rock, in the fault block, is released, and that causes the shaking. Okay, so that's what generates those seismic waves. Okay, and after that, it kind of goes to now you can see how this land is no longer deformed like that. See in that picture up above it, see how the land is kind of being bent. Well, now it's released that elastic energy within it, and you can see that it's gone back to its original shape. Okay, but yet again, what's going to happen is tectonic force will gradually build up again, and you're going to repeat the cycle. So it's just a big cycle, and it goes on and on and on and on and on. And that's why basically earthquakes happen, in the same sorts of places again and again and again. And what controls the rate is how much tectonic stress is building up every year. So you can see this kind of elastic energy being stored up in the ground here. Hollister, California, again, place that's very close to the Bay Area. You can see this curvature in the fence line. That's from the buildup of tectonic stress. Of course, that when they built that fence, they had it straight, but now it's being bent. Someday that elastic energy is going to be released, generating an earthquake. One thing might interest you to know, there's a fault going right through the UC Berkeley. UC Berkeley's in the Bay Area, San Francisco area as well. It's got a fault going right through their stadium, so you can actually see the fault starting to displace the structure of the stadium. So unfortunate for them. Here's another example from California. So a lot of our examples are from California. There's a lot of earthquakes in California. That's because it's an active tectonic boundary. You can see slip in this kind of picture of the grain rows, agricultural rows here, up to 2 feet, right, being displaced. So that's a fault slip that occurred after an earthquake. So when there is movement on a fault, we call that amount of movement slip. So the amount of slip that you see here is about 2 feet. That dot used to be connected to that dot. That dot used to be connected to that dot. Okay. Here's one pretty famous picture of Wallace Creek, again in California. And you can see this creek has been displaced 400 feet, over, I'm not sure how many years, but repeated movements on the San Andreas Fault have moved this creek, 400 feet. It's pretty amazing when you think about it. That didn't happen at one earthquake, but over many smaller earthquakes. Okay. So again, going back to plate tectonics, why do fault blocks move in the first place? Well, it's all part of this process of plate tectonics, right? The plates are moving over the surface of the Earth, and there's a lot of crunching and crumbling and movement along those plate boundaries. So we talked about the 3 different types of plate boundaries: convergent, divergent, and transform, and they all have different kinds of faults that occur on them and different kinds of earthquakes. So at these plate boundaries, right, we have subduction zones, we have these mid-ocean ridges, right, MOR, and we also have transform boundaries as well. So that's not shown here. but those all create their own kinds of earthquakes. So what's pretty amazing is that if you compare a map of the plate boundaries with a map of this is a map of all the earthquakes that have occurred since 1960 greater than magnitude 4. And you can see that the two maps are basically the same. You know, it's pretty amazing how similar the map of plate boundaries and earthquakes is. Okay, and that's because most earthquakes are occurring on plate boundaries. Okay, now of course there are some scattered within the plates. Okay, you can see that there are some earthquakes scattered within the plates, but there's not too many. Okay, so how do we? Another question is, how do we record earthquakes, or how do we measure them? So, you know, back in the day, we had these kind of very simple instruments that had a pendulum with a small wire hanging from a small wire with a pen, and this paper would just be rolled continuously back and forth. And when there was an earthquake, the pendulum would tend to stay still while the earth shook back and forth. So that would create these scratches on the seismic paper that we call seismographs. So we call these things, very famous, I'm sure you've seen these in movies and things, we call these seismographs. Whoops. Gosh, I'm not spelling right today. Seismographs. There we go. So that's how we did it in the old days. Today we have kind of more complex, more advanced, sophisticated sort of things that are able to record wider frequencies of movement. And this is a modern day seismometer. So a seismometer is simply an instrument that creates seismographs and measures seismic waves. And what's pretty cool is we have these things set up all over the world, even in Antarctica. So you have these solar panels that provide energy for the power, and we have these things stationed all over the world. I mean all over the world, right? They're all over Antarctica, North America, Greenland, Australia, everywhere, out in different islands in the Pacific and Atlantic, Indian Ocean. So we have this global network of seismograms that are all connected. And it's pretty amazing, the information that we can have. These things collect information. They're all connected to the internet. And after femtoseconds of an earthquake occurring, we know about it. We know exactly where it is. We know exactly how big it is. And we know where seismic waves are heading. So it's pretty cool that we can give a little bit of warning. We can calculate where a hypocenter and epicenter is very quickly, and we can give advanced warning, maybe not a lot, but maybe 20 seconds advanced warning to major cities saying, hey, seismic waves are going to arrive very soon, so get under a table, get in a doorway or outside or somewhere safe. So 20 seconds, 40 seconds, maybe that's not a lot of time, but it's something to help avoid the destruction that ensues during an earthquake. So we locate earthquakes by a process called triangulation. Okay, so that's how we locate earthquake epicenters. Okay, epicenters are the location on the Earth's surface of an earthquake. Okay, a hypocenter is the location not only on the surface of the Earth, but also gives it how deep the earthquake is. Because earthquakes don't just happen on the surface. A lot of times they happen a certain number of kilometers down in the Earth. Okay, so this is how we figure out where earthquakes occur. We do this process called, like I said, triangulation. And it's based upon how long it takes seismic waves to travel. So there are two types of what are called seismic body waves. There are different kinds of, first of all, waves, seismic waves, okay? You can either have body waves, that's an O, body waves, or surface, okay? Body waves consist of either P or S waves. Surface waves consist of things like Rayleigh or Love waves, okay? So just talking about body waves, there are two types of body waves. There are P waves and S waves. P waves, so body waves, by the way, are waves that are propagating through the whole body of rock, not just the surface of the rock, okay? So there are P waves and S waves. P waves are compressional waves. So the basically what's happening is the rock is being squeezed and let go, squeezed and let go, squeezed and let go, squeezed and let go. The direction of motion of P waves is in the same direction as the vibration. Okay, so you can see that the direction of vibration is back and forth, right? And the direction of motion is this way. So you can see that as this stuff squeezes and compresses, squeezes and lets go, squeeze and let go, squeeze and lets go, it's propagating, it's vibrating in the same direction as it's moving, as it's propagating. Okay. Now that's not true with S waves. S waves are shear waves, and they are moving through the entire body of the rock, going up and down. So the vibration direction is up and down, but the propagation direction is perpendicular. Okay, so I'm going to draw in, I'll draw in blue. Here, let me do this. Maybe this will make it more clear. I'll draw in red vibration direction. So vibration direction for the P wave is, is like this, right? So that's the vibration direction. The vibration direction of the S wave is up and down like this. See how this is propagating up and down, up, down, right? So now the propagation direction, this is the direction the wave is actually moving, is perpendicular in S waves, where it's parallel in the P waves. Okay. Now P waves, the reason they're called P waves is it stands for primary waves. So these are the fastest kind of waves. They're called primary waves because they are the primary or the first wave to arrive at a seismic station. So after an earthquake occurs, first wave that's going to arrive is the P wave. After that will be the secondary wave, which is called the S wave. It is a slower wave that is, again, it's a shear wave. It's going up and down relative to the direction of propagation. So this is a real seismogram. So we can start to kind of break this down and look at it. So the first wave that arrives is P wave. Okay. The second wave that arrives is the S wave. Now the waves that you see here, the big ones, these are the Rayleigh waves. These are the surface waves, okay? But you can see that we can measure pretty precisely when the P wave arrives and when the S wave arrives. Okay? So usually using this time difference, I'm going to put delta t, change in time. Okay? So that's the time difference. We can measure the time difference in the arrival times of the S wave and the P wave and figure out from that how far away the earthquake is. Okay? So because we know exactly how fast a S wave travels and exactly how fast a P wave travels, we can figure out, okay, if it took, I mean, just think of it like this. Let's just pretend P waves travel 10 miles an hour, S waves travel 5 miles an hour. Okay? We know how fast they move. Now, they actually move a lot faster than that, but let's just say P waves move 10 miles an hour, right? And S waves move 5 miles per hour. Again, that's not how fast they actually go. They actually go a lot faster than that, but just for example. Okay? If I know that, there was 1 hour before the P wave arrived, and then an hour later the S wave arrived, I can figure out exactly, because there's a 5 mile per hour difference between these two things. We know that our thing must be 5 times, must be 5 miles away, right? So that would be the location of the epicenter. But of course, just knowing one piece of information like that, it's only going to tell us that, okay, the epicenter is however far away. Maybe it's 1,500 kilometers away or 5,600 kilometers away. So what you need is you need to have three seismic stations to locate the epicenter, okay? Because we know from station A, we know it was 1,500 kilometers. We know from station B it was 5,600 kilometers. We know from station C it was 8,700 kilometers. If we put those all together, you'll see that the 3 circles intersect at one point, okay? With only 2 stations, let's say we only had A and B, we would only know that's either here or here, okay? By introducing station C, then we can figure out which of the 2 locations was the epicenter. So again, world seismicity delineates plate boundaries, right? We have our major earthquakes on plate boundaries. Again, I've showed this picture before. This is showing the ring of fire surrounding the whole Pacific Ocean. Yellow is showing areas of global seismicity and subduction zones. Red is showing, again, where there are specific subduction zones. And the different blue stars show major magnitude 9 earthquakes. So you can see that all of the big magnitude 9 earthquakes have been in the ring of fire over the last like 50 years. Okay, so some big ones here. Sumatra 2004. This is a huge one. It killed over 200,000 people. It's very tragic. Some of you perhaps remember this. It probably would have happened when most of you were kids, but it was a huge tragedy. There was a similarly sized earthquake in Japan 2011, and it killed around 10,000 people. Probably a lot of you remember this one. Japan with the Fukushima power plant destroyed the power plant and created a lot of radioactivity. It was a huge hazard, but very few people were killed in Japan compared to Sumatra and Indonesia in 2004. And a lot of that was because of Japan's very highly sophisticated earthquake detection techniques. The biggest earthquake to ever occur in human history has been Chile 1960. There might have been bigger earthquakes, 1,000 years ago or 2,000 years ago or more, but we simply don't have very good records of them. We haven't had a way of kind of quantifying earthquakes for, which is only recently we've been able to quantify the magnitude of earthquakes. Okay. Alaska 1964 was the biggest earthquake in U.S. soil. You can see that 1906 doesn't even show up here, the 1906 San Francisco earthquake. Okay. Again, one notable place where there has not been an earthquake in the last 50 or actually even 300 years is here in the Pacific Northwest of our country. So the last major earthquake there was possibly in the 1700s. Okay, so we're very overdue for an earthquake in the Pacific Northwest. This is a pretty cool program. You can click on this anytime. This is the IRIS. I can't remember what IRIS stands for. It's something like International Research on Seismicity or something like that. But IRIS is it's an international global seismicity network. But anyway, this is pretty cool. This is a real-time monitor of earthquakes. And as soon as there's an earthquake, seconds after there's an earthquake, you will see it show up on here. So all the earthquakes that are red are earthquakes that happened today. The bigger the circle, the larger the earthquake. So there have been some big earthquakes. Maybe this one right here, I think you can see, was pretty big, right? So where was that? That was around Japan. Okay. So again, Japan's going to have a lot of big earthquakes. And as you can see, the earthquakes, again, are delineating the plate boundaries pretty well. Okay, so little earthquakes, the little purple dot earthquakes are earthquakes over the past 5 years. Okay. So there have been some earthquakes in the Pacific Northwest, you can see. So we had some earthquakes even today in just small ones, just like maybe looks like magnitude 3 or maybe magnitude 5. But there are magnitude 5 earthquakes every day. Okay, magnitude 5 earthquakes every day. There are magnitude 9 earthquakes, which are the largest earthquakes we have, maybe once a decade. This is a pretty cool program. If you want, you can click here and figure out. This is a whole catalog of all the earthquakes that have ever occurred in the last, I don't know how long, 1950s probably. But you can look up whatever earthquake was on your birthday. So I'll put in. I probably shouldn't put in my birthday and tell what everybody my birthday is, but you can put in your birthday here, right here under ending date, and make the starting date the same, and you can look up any earthquakes. So anyway, it's kind of a fun thing to play with. I want to talk a little bit now about what are called Wadati-Benioff zones. So earthquakes don't just happen at the surface. A lot of them do happen at the surface. So this is showing the depths of earthquakes, and you can see that a lot of earthquakes are happening within the first 50 kilometers of the surface. But there's also a lot of earthquakes that are happening underground as well, up to even 600 or even 700 kilometers deep. Really, really deep. And it's pretty amazing that we can actually use seismograms to figure out how deep earthquakes are. So Wadati-Benioff zones are areas where there are very deep earthquakes, unusually deep earthquakes. And what's actually happening is these are at subduction zones. So this particular Wadati-Benioff zone, I guess I don't show it. This particular one is there near the Mariana Trench in the Philippine Sea. So this is showing, you're literally imaging the subducting plate going down. So as the plate goes down, it's still lithosphere, and it's still capable of faulting and breaking and having earthquakes. So once you start to transform into a asthenosphere, that material is so ductile and warm and silly putty-like, it's no longer good at propagating earthquakes. So you don't get earthquakes in the asthenosphere, just in the lithosphere. But this is a really good image of the lithosphere literally sinking and going down. So it's pretty cool. One of the ways that they figure out how deep an earthquake is we actually pick up the echo of the P wave off of the surface of the Earth. So if you look at this P wave shape, okay, you can see the exact shape of that wave. You can actually match it with a. You can actually match it. I can't remember exactly where it is, but they can look at the shape of that P wave, and they can match it like an. Oh, here it is, right here. It's actually right here. It's hard to see, of course. You have to have an expert eye, but you can actually find the echo of the initial P wave strike, the echo of it off of the surface. So that's how they figure out how deep these earthquakes are. And this technique was invented by a Japanese scientist. You know, the Japanese are very interested in earthquakes, as you can imagine, a lot of earthquakes in Japan. So this was research that was done by an American and Japanese scientists, Wadati and Benioff. Okay, so that's the Wadati-Benioff zones. It's just areas of deep earthquakes at subduction zones. Okay, so you can see that the deepest earthquakes, deeper than 500 kilometers, occur almost entirely at these subduction zones, right? So off the western edge of South America, along Japan, and the all throughout the Ring of Fire. I mean, basically the Ring of Fire is almost all subduction zone. It's all Wadati-Benioff zone too. Okay, so moving on to kind of mechanisms, faulting mechanisms that give us earthquakes. So, talked about movement along fault blocks, and fault blocks can move in relative to each other in a few different ways. So one way is extension, and another way is compression, and another way is horizontal motion. So these correspond to the different types of tectonic boundaries. So remember, at divergent boundaries, pardon me, at divergent boundaries, the plates are moving apart. At convergent boundaries, they are moving together. And at transform boundaries, they are moving side by side. Okay, so you're going to see we have three different kinds of what are called faulting mechanisms at these three different tectonic settings. So in places where extension occurs, so where the plates are moving away from each other and diverging, we get what are called normal faults. So you can take a look at the angle of this fault, and you can see that one of the fault blocks has slipped down the angle of the fault plane. Okay, so you can see how this fault plane is sort of at an angle. One of the fault blocks has slipped down while the other has slipped up. Okay, so that's what's called a normal fault. Now during a compressional fault, you go to where it's called reverse. Okay, in this case, the what's called the hanging wall has moved up relative to the footwall. Yeah, so that's probably a good way to refer to these things. So this fault block is called the footwall. This one is called the hanging wall. And this terminology comes from the days when mining days. I mean, they're still mining, of course, but old mining days in which a lot of economic deposits that were being mined were occurring along faults. And when miners would walk along the faults, you could imagine a person right here kind of climbing up this fault here. His feet would be on top of the footwall, and he would hang his lantern on top of the hanging wall, okay, which would be above him. So the hanging wall is kind of is this kind of basically, if you were walking up the fault, you'd be walking on the footwall. The hanging wall would be the other fault block. So in the normal fault, the hanging wall is moving down. In the footwall is moving up. Okay. In the reverse fault, you get the opposite. So the hanging wall is moving up the slope of the fault plane. The football is hanging or going down, moving down. Now in a strike slip fault, there's just horizontal motion. Okay, so this is called strike slip. So that's at a transform boundary. Okay, so places where you get extension and divergence, you're going to get normal faults. Okay, so you can see here a lot of the faults in the I talked a little bit about before, remember, this is the, gosh, what's it called? The name is escaping me at this time. Sorry. Gosh. Sorry, my mind is blanking. What is this area of the western? It's called the Basin and Range. Gosh, sorry. Basin and Range. So this Basin and Range province, which takes up a lot of the western half of our country. You can see all of these little mountain ranges in Nevada. It's actually all over. It's Nevada, California, Arizona, Colorado. I mean, it's all over the place, all the way up to Wyoming, even as far north as that. So you can see all these little mountain ranges, right? So all these little mountain ranges are places where normal faults are occurring. So this is a very typical, what's called, another term for this is Horstengraben. So Horst is again, it's a German word, so it's kind of these elevated areas. The Graben, like the grave, is the lower area. So you can see when you have normal faults, part of the land pops up, part of it sinks down. Okay, and that's what creates this Horstengraben or Basin and Range. So areas that have experienced, you could see that here too in this picture of the mid-ocean ridge. You could see the little Horstengraben, right? So Basin and Range. And that's just very typical of places where there's extension, places where the normal faults are occurring, and you're getting divergent boundaries. Okay, so actually this Basin and Range has literally created the state of Nevada. So this is what 20 million years ago the western half of our country used to look like. And look at Nevada was really scrunched up. So 20 million years of extension has made Nevada look a lot fatter. You can see that, right? So that's all from this Horstengraben extension, Basin and Range extension. Here are some strike slip faults. So you can see the fault line going like this. Now this is what's called a right lateral strike slip fault, and that's because a person kind of looking across the fault will see things move to his right, and a person standing on this side of the fault looking at stuff will see things move to his right, okay, his or her right. So that's what's called a right lateral strike slip fault. Okay, the San Andreas fault, for instance, is a right lateral strike slip fault. Okay, here in Taiwan, right? Taiwan is of course getting some action from the whole Himalayas and the compression coming from the collision of the Indian subcontinent with the Eurasian continent, and we get a lot of reverse faulting, right? So we get a lot of fault blocks moving up, others moving down relatively to that, in relativity to that. Okay, so the largest earthquakes, though, that actually occur along subduction zone trenches. Okay, and these are what are called megathrust earthquakes. So megathrust earthquakes create the largest earthquakes we have. These are the one that create the magnitude 9. Okay, size. I want to find. I showed you this before. There was a little GIF I want to show you though. Hold on one second. I'm going to pause this. Okay, so IRIS puts out a lot of videos that are very good, teaching you about seismic waves. This one is just a little animation kind of showing how these megathrust earthquakes occur. and how they're very dangerous because they create tsunamis. So this is like the very famous tsunami in Japan 2011, the devastating one in Indonesia 2004, Indonesia and Sumatra. These were created by megathrust earthquakes from the subduction zones off their coasts. Okay, so I'm going to show you this. This is a pretty good video about it. Let me turn up the volume here. Okay.
Subduction zone megathrust earthquakes, the most powerful earthquakes, can produce tsunamis through a variety of structures that are missed by simple models. The basic model shows rock above the convergent plate boundary being compressed and bent as it stores elastic energy. Once friction is overcome, the overriding plate slides abruptly up the fault, causing the leading edge to heave seawater upward, generating a tsunami. This shallow angle reverse fault is called a thrust fault because the overlying plate thrusts up over the subducting plate. Let's explore different tsunami-producing mechanisms by examining 3 famous earthquakes. In 2011, the magnitude 9 Japan earthquake ruptured a fault area 500 kilometers long by 200 kilometers wide over an interval of nearly 3 minutes. Surveys of seafloor bathymetry before and after the earthquake document up to 50 meters of fault displacement at the Japan Trench. What would that look like in cross-section? During the rupture process, the overriding plate slid up the west-dipping fault plane. That uplifted the seafloor by 10 meters, producing the local tsunami that rushed on shore within 20 minutes of the earthquake.
Yeah, so that's crazy stuff, right? So the seafloor in some parts, number one, the seafloor moved 50 meters, okay? So quite a lot. And then after that, it displaced the water 10 meters. Okay, 10 meters is basically about 33 feet. So this is the thing about tsunamis that are so devastating, is that when tsunamis are created, we're used to waves that are basically surface waves. Okay, so it's just the surface of the water being usually driven by the wind. The surface of the water is moving, and it's just superficial, right? It's just the surface. With a tsunami, the whole ocean is moving. The whole cross section of the ocean, from the bottom to the top, is moving. 4,000 meter column of water is moving. When that happens, so the water comes in. It's kind of like, imagine having a temporary rise in sea level of 33 feet. Okay, it's huge. So what happens during the sea tsunamis is the water starts coming in. A lot of times you can't even see the wave. It doesn't even look that big. The water starts coming in and it doesn't stop. It just keeps coming and coming and coming, because it's not just the surface of the water that's moving. It's the whole thing. I'm going to pause this another time. I just want to show you some pictures of the Japanese tsunami because they're so amazing and terrifying, actually, is what they are. Okay, so this is just, you might have seen this video before, but this is my favorite one of the Japanese tsunami, where it overturns the seawall, the break wall. But anyway, it's amazing. This is a 15-minute video. I'm not going to show you the whole thing, but in case you haven't seen this before, it's amazing because you don't really even see anything that's particularly alarming. It's because the wave that comes in has a very long, basically a very long wavelength. Okay, so it's the crest of the wave. What am I trying to say? I'm trying to say that this wave, it is a wave, but we almost don't see it as a wave because the wavelength is extremely long. It might be a mile long. So you just start to see, you can see right here the wave is just starting to come in, and it seems, maybe not very alarming, not that big of a deal. But if we start to go forward in time, okay, we go forward maybe 3 minutes. Now you can see things are starting, the water's starting to come in. And again, it's because the wavelength is so long of this wave, you don't really realize what's going on. So you can see the water level starting to rise. The boats are getting unmoored. We move And you guys hear that people are screaming. They're trying to warn people to get out of the streets because they know what's coming. I mean, what this person is doing down here is extremely dangerous. They need to get out of there. So you move a little bit further down. So now we're at 3 minutes. Okay, you go to 5, about 6 minutes. You can see that by what? By 6 minutes, that break wall is flooded over. So now it's kind of like the crest of the wave has finally arrived. So you can see that the wavelength, it's 6 minutes long from the crest to the very beginning of it to the crest. So it's a very long. See, we're not used to thinking of waves in the ocean that way. You know, tsunami waves are very different than the normal superficial waves that we are used to. And you know, the thing is that the water just keeps coming. You know, it's going to keep on coming for another 12 minutes. It's going, you know, water levels are going to continue to increase. And you can see what happens. You know, everything just gets totally swept away. So it's an amazing amount of power. Very terrifying. Now, like I said, what happened in Japan, about 10,000 people in Japan were lost, which is a tragedy, but it's also a miracle that there weren't more. I mean, like I said, in 2004, just, you know, a couple of years before this, there were over 200,000 people died in the Indonesian tsunami. You know, it's like the earthquake doesn't actually kill that many people. It's the tsunamis, okay? So those are megathrust earthquakes. They're the worst, most powerful, dangerous, deepest earthquakes that we have. So anywhere where there's subduction actively occurring, it's very dangerous. This is a 2015 Nepal earthquake. This is also a pretty big earthquake. It wasn't quite as large as the 2011 Japan earthquake, but again, this is a reverse faults from the collision of India with Tibet, right? So that's what created this very devastating earthquake, and the compression and compressive waves traveled all throughout China, so those things could be felt very far apart. So a lot of earthquakes don't leave a scarp at Earth's surface. Actually, a lot of earthquakes are happening pretty deep. The faults don't even make it up to the surface, believe it or not. So a lot of times you don't see these what are called scarps. Scarps are the actual scars left on the surface where you can see the displacement. This is a shot of downtown Los Angeles. The beautiful San Bernardino Mountains that are just north of downtown Los Angeles are created by a similar compressional reverse fault there. That's right at the base of the mountains. You can see the downtown at Los Angeles City Hall right there. So anyway, this is extension, right? Creates your normal fault earthquakes. Compression creates your reverse fault earthquakes. And transform areas create your strike slip earthquakes. Okay, so transform faults, right? You know, either going to have right lateral or left lateral strike slip faults. So this one that you see right here is right lateral. And again, looking at this one, this is a strike slip fault displacing Wallace Creek. I've showed you before. Again, this is a right lateral because looking at the creek from this side, we see the creek moves to the right relative to this side. Okay. So just some kind of possible exam questions you might see. What is an earthquake? So an earthquake is frictional sliding along a planar surface. Earthquakes occur when stress on the fault plane exceeds the frictional strength of the fault plane. Okay. Why are earthquakes this should say why. Sorry. Why are earthquakes cyclical? It's because of elastic rebound. Okay. When I asked this, I think I probably asked this on the lecture assignment, don't say elastic rebound theory, okay? Elastic rebound theory explains why, but nothing actually happens because of a theory, you know? Theories explain things, so when I ask why are earthquakes cyclical, you should explain for me elastic rebound theory and why it seems to say that they are cyclical. It's because tectonic stress is always building up in the same area. So tectonic stress builds up, it deforms the shape, builds up elastic energy and deforms the shape of the land. Once the tectonic stress exceeds the frictional strength along the fault plane, that elastic energy is released. That's the elastic rebound, and the rocks go back to the original shape, and tectonic stresses again are still active in the area, and they start to build up that stress yet again, and that's why earthquakes repeat again and again in the same areas. Where do earthquakes occur? You should know that. And basically all you need to say is they occur along plate boundaries. That's enough said. What are Wadati-Benioff zones? They're areas where you have very deep, maybe greater than 35-kilometer deep earthquakes. And that's all you have to know for this, right? Well, that's not all you have to know. You have to know the whole lecture, but those are just some exam questions that could show up on your final. So anyway, that's all I have for you today. I hope you enjoyed the lecture, and I'll talk to you next time when we study volcanoes.